Welcome to our viewers. There is clear opportunity for electrified aircraft, both today and also just over the horizon. Not only will it wean the aerospace industry off of fossil fuels, but the complexity of aircraft avionics and creature comforts demands more electricity with each generation. That means more energy storage and higher distribution voltages and currents in each circuit. This is by no means an easy equation to solve. Every additional pound of circuitry reduces aircraft range. Complex installations mean longer and more expensive manufacturing. Of course, safety is paramount in any aviation application. In the aerospace environment means climate extremes and challenging shock and vibration. TE Connectivity has a broad, complete portfolio of high-performance relays and components for the aerospace industry. Together with their strategic partner Powell, they make it easy to understand and obtain the components needed to innovate in the aerospace industry. Joining me to discuss these challenges and the technologies to help overcome them is Eric Weingartner, Senior Product Manager for High Performance Relays at TE Connectivity. Eric has over 21 years of experience in electrical power distribution for aircraft and has developed a variety of AC and DC power switching solutions for both military and commercial aviation. Hi, Eric. Thanks for joining me today.
Hi, Kevin. Thanks for having me. It's great to be with you.
My first question for you, Eric. What is the significance of the more electric aircraft trend, and what does it mean for onboard electrical distribution?
The significance really is that power budgets are going up. And if you imagine historically aircraft that might have used hydraulic systems that are now moving to using electricity to perform the same work, they're getting away from some of the heavier, bulkier components of hydraulic, as well as the maintenance requirements, and using more and more electricity to do the same job. And typically, when we need more power, we're either going to get at that with voltage or with current. And if I increase the current, I'm going to have to also increase the wire gauge that I'm going to use on that aircraft, which is going to have a major weight impact, particularly on longer wire runs. So typically, this means that voltages are also going up. And in general, across the aircraft, what it really means for us is more and more applications are using electrical power on the aircraft. And for us, this is really exciting because at TE, we believe every connection counts. And this trend really gives us that opportunity to make those connections for our customers every day.
Where do relays fit into the electrical system?
The relay is really at the heart of the switching. And I like to use the analogy of your circulatory system, for example. And we have our heart, which is where it all starts, and it's pumping larger volumes of blood through those arteries, the main vessels that are coming off of that source. But as you travel down through the system, you're getting down smaller and smaller vessels and all the way out to the capillaries that are out in the tips of your fingers. And the electrical system is very much in the same way. You're seeing a couple of engines up behind my shoulders on the background behind me, and that's really where it's all starting. And those engines are turning generators, which are pushing electrons throughout the electrical system. And with relay product, we have to switch power that's more in the primary power arena. That's large numbers of amps that are coming right off the main power sources. But once again, as you travel down the wire and you go through to the end of that electrical system, you're getting to smaller and smaller power levels. We're getting into secondary power now, and all the way down to those individual loads that need to be turned on and off. The load might be a landing gear light. It might be a coffee maker in the galley. It could be your in-flight entertainment system that's on the seat back in front of you. But all of those loads have to be switched on and off. And so we think of relay requirements in terms of control, things that I need to turn on and turn off. Another way you can think about it as well is with waterworks and faucets and valves, the spigot on the side of your house. There are times when you want that turned on and you want water flowing through your hose for whatever use you have in the backyard. But there's times when you need to turn that off. And it's the same in the electrical world. Relays are used to control loads, turn them on and off. We also think of them in terms of isolation. So That's removing harmful voltage from a user interface. And the last way we tend to think about relays is in terms of distribution. So they literally distribute power all throughout that aircraft. You can imagine if I incurred some damage or a failure at one part in the circuit, the question becomes how can I reroute power and get it to that critical load in the case of that fault? And the relays are what are going to perform that distribution.
What are some of the design challenges for aerospace relays? And do those challenges make it tough to innovate?
Yeah, because every pound corresponds to fuel efficiency, making the product smaller and lighter is key. And anyone can cut material out of a product, whether you're cutting out of the conductors, whether you're cutting material out of the iron that's in the magnetic circuit of the actuator itself. But that's of course going to be at the expense of performance more often than not. So the challenge is really to reduce size and weight and not compromise on the performance. And as you alluded in the introduction, these are in some pretty rugged environments, shocks and vibrations, temperatures, extremes. And so we absolutely can't compromise on performance. And that's where we really love to play in terms of providing those highly engineered solutions that will reduce size and weight and still deliver the needed performance. Another aspect, as I mentioned with power, it's the product of volts and amps. And so unless you want to run big, heavy wire through your aircraft, you're going to increase voltage to get at more power. And we're certainly seeing that trend with electrification. The challenge also is to switch and to isolate higher voltages, both safely and reliably on the aircraft.
What are the advantages of a solid state relay versus an electromechanical relay?
Yes, solid state is an interesting technology, and the principal advantage it brings is high speed switching. And by that I mean solid state devices tend to switch in terms of microseconds of time, where an electromechanical device is going to switch in milliseconds of time. And so just rough cut comparison, we're talking about 1,000 times the frequency, the high speed capability of a solid state device. We talked about voltages going up in the system. I want you to imagine that you have a short circuit on the line. There's that much more energy that can be dumped into a fault and cause a lot of damage very, very quickly. And so we can appreciate the need for a very high frequency response. I would rather clear that fault in terms of microseconds than milliseconds when there's that much energy going in and causing damage to wire, to conduit, to aircraft structure, whatever have you. And so the principal advantage, of course, is high speed with solid state. But we also should remember that with solid state, there's really no moving parts. It's material that's more or less turned on and off. And so you think about in terms of reliability. I'm not taking a pair of contacts and literally mechanically banging them together. I'm not moving them back and forth in some sort of whatever geometry that you're working on with the relay. There's always that electromechanically, there's always that motion back and forth, which corresponds to a mechanical life. Things will tend to wear over time. But solid state with no moving parts can bring higher levels of reliability to the system as well.
So then will solid state ultimately replace all of the electromechanical requirements?
It's a good question. And in my 20 plus years, based on that experience, I would say no, they're not going to ultimately replace all electromechanical devices. There are applications, and those applications might be controller type applications where there's rapid cycling on and off that might lend themselves to solid state. We talked about the fault scenarios as well and how quickly they can respond to them. But there are applications where the galvanic isolation of physical contact separation is critical. If you think, for example, with a battery, maybe a high voltage battery, where its safety becomes a concern. The solid state device is always going to have some leakage across it. Once again, there's no moving contacts. It's material that's more or less turned on and off. You could also imagine a critical application such as firing a missile or some type of a weapons fire application. The last thing we want to incur is an inadvertent weapons fire. Once again, having a device that will always have some leakage going across it may not be the optimal solution for critical applications like that. And the last advantage that I'd like to highlight that electromechanical still tends to bring to the table is it has the inherent capability of having, in general, a lower on resistance than solid state. The solid state devices tend to drop a little more voltage. They tend to be a little more resistive. And that corresponds, when you're carrying current for an extended period of time, that corresponds to heat production. So they'll produce more heat for the same power going through them with their higher resistance than an electromechanical device. So applications that are sensitive about thermal and heat generation would also tend to still look to using an electromechanical device.
How does TE address power consumption in the relay?
So there's a couple of ways that we tend to address that. I talked about size and weight. I'd like to talk a little bit about efficiency within the device. So relays use a magnetic circuit, an electromagnet electromechanical relay will use an electromagnet to turn on and off to achieve the motion. So I want you to imagine the magnet drawing up to your refrigerator. That's a permanent magnet. It'll never turn itself off and drop to the floor. But I want you to imagine when we put a coil in a relay, we have the capability of turning a magnet on and off. And that's how we essentially accomplish the switching motion of the relay. And if I have to carry more current and switch higher power, I need more forces in that actuator. The actuator has to be larger, has to have more cross section to deliver more magnetic force, essentially, to handle those higher forces. So one of the ways that we reduce power consumption in the relay itself is making those actuators more efficient, so that you don't have to deliver, as the customer, quite so much electrical power in the coil, consuming more power, and you can still get that force that you need out of the actuator. The other way, in much dealing with the same principles, we use latching devices. And these are products. A latching relay is a relay that will stay stuck or latched in the last position that you commanded it. It does not need continuous coil power going through the coil in order to keep it in that state. And if you think about, let's just take the example of an eVTOL. It may be single-digit number of miles that it's going to be flying on battery power, electric propulsion. So there's no jet fuel, and it's not, engines aren't burning to produce electricity. You're strictly consuming that off of a battery on board. And it may be single-digit miles that you're going from a city center to the nearest airport, where that executive is going to get there very quickly without having to sit in traffic. But I want you to think about that scenario where you've got batteries and that's your budget on board. So the less components that are being parasitic and consuming power continually on those batteries, the better off you're going to be. So in these types of applications, and satellites happen to be another one in space, latching devices are in high demand. And that's another way that we really limit the power consumption in the relays.
Can you provide more detail about TE's smart connectivity solutions?
Sure. Let's say you have a relay installed in the aircraft and it's rated for 100 amps. And that means it can carry that 100 amps all day long. It's been designed for that. It's rated for that. But the question becomes, what happens if there's 150 amps flowing through the device? Well, you might say, if it's a second or two, probably not a big deal. If it's a few more seconds long, it's probably still not a big deal. But I think we'd all agree that at some point in time, if that 150 amps doesn't go down to 100, we're going to be getting too hot. We're going to have a thermal situation. We're going to start degrading materials and damaging components, wire on the aircraft. The load itself could be damaged on an overload situation. And so what we do with our smart connectivity solutions is actually embed sensing devices. And in this particular example, it would be current sensing. So we would have the ability to sense that uptick into 150 amps, and we would know that we're in an overload situation. And we could provide electronics that autonomously controls the tripping and protection of that circuit. And in our example, the 150 amps might be able to stay on for 10 seconds, 30 seconds, whatever that time would be. We can work that out with the customer. And if it's much higher current, the times are going to contract and become much smaller, to where you may have an outright fault on the line, and we'll just trip open almost immediately and protect, once again, the circuit from that very harmful fault. And so this becomes a way that we can embed sensing, and we can sense voltage, we can sense frequency, we can sense phase rotation, and sense current, as I said, sensing a variety of parameters, and can provide that autonomous protection, which means we also don't rely on the central intelligence, if you will, on the aircraft itself to tell us when to open and close. This is something that a customer can tuck away in a corner someplace, and it's going to provide that protection autonomously of its own accord.
Very interesting. Why should a customer consider using a power distribution assembly?
If the customer happens to have the flexibility to invest in a custom assembly, and I say that if on the front end, because there are times when customers need something off the shelf quickly, but when they have the flexibility to invest for us to design and develop and qualify a customized power distribution assembly, the advantages are we can save them a lot of footprint on the aircraft. I want you to imagine all of these components that oftentimes are strewn throughout the aircraft, and we're taking all of that footprint and we're consolidating it into a succinct panel. And secondly, I want you to imagine the scenario where the customer has to install each of those components individually all throughout the aircraft. Could be several dozens of components just to bring out a scenario, and every single one of them having to be installed on the aircraft. What we deliver when we deliver a power distribution unit are all of those components already installed in the panel assembly. So I want you to imagine the touch labor that saves on the installation. And I'd also like to just highlight that within TE, and we're talking about relays today, but within TE, we have connector product, power signal for the I/O that comes in and out of that box. We have board-to-board connectors, high-speed data connectors. We have rugged fiber optics products. We have all the wire and cable products that connect from point to point. We have the harnessing products, all of this within TE. And this is all expertise that we bring to the table in designing this optimized and customized solution for the customer.
Eric, a wealth of knowledge. Thank you so much for sharing some of it with our audience today.
Thank you for having me on. It's been a real pleasure.
Awesome. Viewers, stay tuned so you can learn about TE's aerospace relays and how to get them through Powell.